just turn that on. All right. All right. So I'll go through the steps again through the video if you actually need it. Some of you may not need it at all. All right. So we're going to blame Janelle for that one. All right. So we saw for y. We're going to substitute that in. So we substitute in. We get x times 40 minus 2x. Then you just double check. You should only have one variable when you optimize. Okay, only one. My variable here is x. I always say simplify it if you're doing an optimization problem so that you don't have to do extra rules. I don't want to do a product rule. Therefore, I'm going to simplify this by multiplying it out so that I just get to do powers. Other things. Did I take a derivative at all? No. Which means you better label every step you do so that it doesn't get confusing, and IB is much more specific about it. So please make sure you label your work. Don't just randomly write things. I hate seeing this. I can't tell what you actually did. You're supposed to always tell me what you're doing. And that is important, okay? Across the board, you always write what you're doing. So, in this case, now we have, it's simplified as much as we want it to be simplified. And now I can find my derivative. So there's my first derivative. Set it equal to 0. The nice thing about optimization, I have a tendency not to really worry about the undefines. It's a real life problem. Would you ever want your area to be the derivative of your area to be undefined? It's rarely the case that you end up using those values. I still do it just for being consistent. So, what do we get? We get x equals 10. So then you go back and you double check. Let's just really double check if 10's really going to give us a maximum. So there's my A prime sign chart. If I put 10 into my derivative, I do get 0. But if I put, say, anything to the left of it, 0, I get a positive. Put 1,000 into my derivative, I get a negative. Therefore, I am guaranteed that that's a maximum. So that is my maximum. Anyone know what else you should check anytime you do max and mins? Not just where the derivative is 0. The endpoints. Are there any endpoints? I'll tell you the easiest way to check for an endpoint. Can either of those ever be 0 in the problem? No. Let's see. If you know that, you can guarantee you probably don't have endpoints. It's a cheap way to check. So I just look at the variable and I think about, can x equal 0? Because if it can equal 0, you probably have endpoints. If it can equal 0, you probably don't have endpoints. So I always do my first derivative and I check my endpoints. In this case, we don't have any. So there's my maximum. Am I done my question? What did it ask me for? The actual maximum area. So you just want to make sure that when you're all said and done, you answer whatever they asked you for. And I'm going to do that here. So I would need the area at 10. So the area at 10 is some value. What, 400 minus 200, 200? Is that right? Okay. And then feet squared. Things that you want to try to remember. Try to remember your units. Okay? Easy question. Goes through the steps. So as much as I didn't record the first few steps, I'll say them all as we go through. All right? Any questions on a basic optimization problem? Okay? We're going to follow the same exact kind of steps going through. The situations will change. The second one. What dimensions for a 1-liter cylindrical can will use the least amount of material? And I always give this one because a lot of people get confused on what that means, amount of material. So first thing is, what's my question? Minimum surface area. So I'm just going to use A for area again. And then in the end, my real question will be the dimensions. So you just want to make sure at the end you answer whatever they asked you for. All right, so surface area, cylinder. I believe you guys get these formulas in that packet, so you don't have to memorize them all. Area of a cylinder would be 2 circles, the top and bottom, plus the soup label. Soup labels are rectangular. The rectangle is created by the circumference, 2 pi r, and then the height. So the surface area of a cylinder does make sense. Then you look at what you have. There's one variable, there's two variables, so there must be more information. So I'm going to come over to the right here. What's that extra information? Yeah, the volume thing. So they tell you it's 1 liter. 1 liter is the same as 1,000 centimeters cubed. That should make sense to you. You don't ever measure distance in liters. I can't say that a football field is 15 liters. Makes no sense. So we have to change our liters into a cubic distance to make sense. So my volume, which is 1,000, the volume of a cylinder, area of the base, pi r squared, multiplied by h. Okay? So what do I want to do with this guy over here? What should I do? Substitute it, solve for what? H. Please don't solve for r. Please. That is not the smart way to go. Alright. And then once you get that, we're going to substitute that right in here. So what do we get? We get that the area is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And then simplify it. Don't leave it like that. You want it simplified so that the derivative is easy to do. So that's 2,000 over r, which is the same thing as 2,000 times r to what power? -1 is correct. Good. All right. Take the derivative. Set equal to 0. Set equal to undefined. Go through the rest of the steps and try to find an answer. And then I'll go through it real quickly. So most of you got your derivative, correct? And you got up to here is my guess. Double check that you have a negative. Double check you have an r squared. You want to simplify your derivative. You don't want to solve these the way that they're sitting there. You always want to get a common denominator in a derivative. Not in your original, in the derivative. So, common denominator would make this be multiplied by r squared over r squared. Does that make sense? Alright, so what does that look like? 4 pi r cubed minus 2,000 over r squared equals 0. If you remember from calculus, the reason we do that, it's very easy to do a sign chart because you take the numerator, set it equal to 0. Those are your zeros for your derivative. Then you take your denominator, set it equal to 0. Those are your undefineds for your derivative. So when I say simplify and there's a fraction, you get a common denominator. It makes solving for your derivative values a lot easier, your critical values. So, if I want a prime to equal 0, or I want a prime to equal undefined, it makes it very easy. Here's the numerator, here's the denominator. In this case, you can't have a radius be 0, you wouldn't have a can. What else does that tell us? Not only can the radius not be 0, now, as a result, what do you not have to check for? Endpoints. So r can't be 0, no endpoints. Like I said, it's an easy, cheap way to know if there's endpoints. This is the only one you have to worry about. What do you actually get? 4 pi r cubed equals positive 2,000. Oh, that doesn't say 2,000. Alright, it says 20,000. Alright, and then what do we get for r? We get the cube root of 500 over pi? Does that sound right? Yeah? Okay. So, is that my answer? No, what did they ask me for? Dimensions. So I got my r. Easiest place to find h? Where you solve for it. Every single time it works out nicely that way. So now I would substitute into here. Leave it as the value that you get ends up being 1,000 over pi multiplied by 500 over pi to the 2/3. Ugly, but it's an exact answer. Okay, your exact answers are exactly what it says. Exact, no decimals. If you get a calculator, throw it in the calculator. Okay? Let's talk about if you get a calculator, because the rules for the IB test are way less strict. So on your IB test, let's actually start with AP. On an AP test, if you were given a calculator, you would still be forced to do the derivative, and you would have to show the derivative. You could use the calculator to find the zeros, but if you use your calculator to physically show just what the maximum or minimums are by substituting in this function, it would be incorrect. You wouldn't get full credit. Whereas on the IB test, you get to do that. What do I mean by that? Let's say I give you the calculator. I would stop right here, and I would graph that. And when I graph that, what would I look for? I would look for the physical minimum on that graph. So what I'm covering right now, it wouldn't even show up on your paper. You wouldn't do any of that. So I would find the physical minimum on the calculator. That will give me my x value. And then I would need to go back and find my h value. It makes it a lot easier when you get a calculator. So I want you to realize that on the IB test, they are a lot less strict about what you get to do with your calculator. You get to use everything. On the calculus test, for those of you in BC, you cannot use the max and min functions on the calculator and get credit for it. Okay? All right. So this one is from your textbook. I'm using it because it's similar to another problem that we do, but set up very differently. So it says, find the maximum area of a rectangle inscribed in an isosceles right triangle whose hypotenuse is 20. This one is set up so that you want your triangle to be this way. Isosceles means this side and this side they're going to be the same. How much are your angles then? 45. All right, so I want to inscribe a rectangle. I have no idea how big the rectangle is. I'm hoping the picture is not exactly on the same page. If it is, just cover it. All right, so there's my rectangle. We don't know how big the rectangle is. So what should I label the bottom of the rectangle? X. All right, sure. And we'll call that Y. All right. So find the maximum area of the rectangle inscribed in isosceles right triangle. So let's start off with the fact that I am going to maximize the area of a rectangle. And given the variables you gave me, I have that. So I'm stuck. There must be more information. What's the more information they gave us? Hypotenuse. So this whole entire thing is 20. I have to write an equation. Once you figure out an equation with the 20, that's all you actually need. You just need some type of equation. Something to substitute in. Let's see. I need hands because you're going to give me like specific things. Yes, Rebecca. So the whole minus this would give me these two pieces. How does that help me? So these two together are 20 minus x. How much is one of them? How much is one of them? Say that. Luke, go ahead. Over 2. Okay. So this piece, so I'm taking what Rebecca said. I'm going to add in, let's make it 10 minus x over 2. Okay. I just took what you said and did it for both sides. So this little piece here would also be 10 over x minus 2. All right, so that didn't help me just quite yet. Anyone? I'm not giving it to you. It's okay to be wrong. Cut the isosceles in half? Okay. Okay. Yes, that's true. Everything you say is true. You're going way deeper than you need to. But everything you said is true, and at some time, like a half hour later, you would totally get the answer. It would work out. There's something really basic you guys are missing. So, does it make sense that once you figure out what y is in terms of x, you can substitute that in, right? We're looking for an equation. Alan, what do you think? I could. I definitely could. Which is 1. Yeah. You want to do SOHCAHTOA. You want to use opposite over adjacent, I'm assuming, to find the value of this, correct? Well, there's a much easier way to do it. That's what I was hoping you would say. How much is it? Come on, people, if they're 45, 45. This side is opposite the 45. This side is opposite the 45. What does that mean y is? This is what I said, Luke. You would have gotten there at some point. You were using the relationship just in the bigger triangles instead of the smaller one. Ah, I found it. There we go. Throw that in, you got it. The setup for this one I thought was tricky. And then I think the picture of it is somewhere there, right below, but it's tricky. It's not, when I think of an isosceles right triangle, here's mine. Every single time I draw mine, I always draw them that way. So I found it interesting that for this one, you wouldn't want to do that. That's why I showed it. That's the whole reason. I'm not going to go through the process, okay? Because the process is the same. Look at the next one. Oh, there's the picture. I knew I had it somewhere. All right. All I want is just the setup. I don't want to go through the process of the derivative set equal to 0 and so on. I just want the setup. I don't need an answer. I want them to know how to do it. That's ridiculous. All right, so it's really interesting that there's so many of you that can't find the surface area. So just so you understand, the basic concept of surface area is not hurry up and look for a formula. It's understanding, hey, listen, it's understanding what surface area gives you. Because just for the cylinder, I did the same thing. I didn't memorize the formula. I said how to find the surface area. So for this one, the surfaces, there's 5 of them. Let's start with the bottom surface. It happens to be a square. And then there's 4 other sides where every single one of them, the base is x and the height is h. Therefore, there's 4 of those. There are your 5 sides. Okay? That's not the information I needed to start, but I noticed that's where you guys got tripped up. There's the information that's needed. So this, I would use area, which was how much? 108. Please solve for h. Yeah, did I make a mistake? No. No. Where were you trying to subtract it from? From the volume or from the area? From the volume? Nope. Volume won't matter. All right. All right, so substitute that in. Same thing, though. Simplify it as much as you can before you try to do a derivative so you don't get stuck having to do hard derivatives. All right? That was number 3. Let me see if I want to set up any others. Have you guys seen this one enough that I don't need to do it, the cardboard box? Yeah, so this one is where you cut out the corners. And you make the corners x. So this side is 14 minus 2x. This side is 10 minus 2x. And then the height is the x itself, because that's what folds up. So length, width, height. Or length, width, height. It actually doesn't matter. We did with me. All right? So I'm not going to go through this one. I always show this one because there aren't necessarily 2 variables unless you actually start with the volume formula. If you start with that because you're finding the maximum volume, it'll make you think that there's 3 variables. But the x is what you relate all 3 with. Okay? That's the only reason I give that one. And then this one, same thing. A lot of times they don't give you the picture. If they don't give you the picture, you have 2 different options. You can make well then, thank you. Alright, so you can do this. You actually do have the option of saying the whole paper is x and y, which changes it changes your work a little bit, but in the end your final answers are exactly the same. So I just wanted to show you that. Once you figure out what the question is and you draw in the picture and you put in your measurements, it's usually pretty easy to figure out the answers. Those are pretty much the basic optimization problems that you get. You do want to look at the examples in your textbook. I don't think you need to do the last one. I think the last one is above what you guys will get. But those are the basic examples that show up in almost every textbook. These are all your derivatives. It was nice to kind of have them in one place, so I wanted to show you that. It also gives you what they call the first principles, the quotient, the difference quotient of a derivative. So that's there. And then I just wanted to make sure to quickly go over your first derivative test and second derivative test, which you did with Mr. Ish. Just making sure that you understand that critical values are where the derivative is equal to 0. Oh, I should put an or. Or undefined and endpoints cannot be critical values. Endpoints aren't critical values. Even if the derivative is 0 at an endpoint, it can't be a critical value. It's part of the definition of a critical value. Things to be careful about when looking at max and mins. So your maximum can happen, and your minimums can happen. We're going to do interior. I'm going to make kind of like a table. Endpoints. So maximums will always happen in the interior if your first derivative sign chart looks exactly like this. Right? You know that. Your endpoints, be careful. A left endpoint versus a right endpoint. A left endpoint and maximum happens when, and these are still part of the derivative, left endpoints that are maximums, the function would then have to go down after that. So it makes sense that this would be the sign chart for a left endpoint max. A right endpoint max, the graph would have to go up, therefore. Does everyone understand that the endpoints are different than an interior? Okay. All right. Therefore, the minimums, same thing. Derivative signs have to change minus to plus. They have to be in that order. And in terms of endpoints, your left endpoint, if you want it to be a minimum, the graph would have to go up after the endpoint. Right? And then if I want my right endpoint, the derivative, because the graph would have to go down to the endpoint, would have to be a minus. Right? Stuff that you know. Just wanted to be clear with the critical values. The only thing I want to go over for your second derivative test is actually what it is. Most of you don't use the second derivative test is why. So, if f double prime of a is not equal, is greater than 0. What am I doing? No, I lost my if. Let me go in order. Oh gosh, erase. Alright, if f prime of x is equal to 0 and f double prime of x is greater than 0. And then the other one is if f prime of x is equal to 0 and f double prime of x is less than 0. So, this happens, but you have to be concave up. So let's draw something that's concave up. The only place where the derivative is 0 would be down here. Therefore, this gives you a minimum. The combination of those two things gives you a minimum. Draw something that's concave down. Label the only place where the derivative is 0. Happens to be here. This gives you a maximum. And then I always have people ask me, well, what happens if f prime of x is equal to undefined? Can't use the second derivative test. What if f double prime of x is equal to 0? Then you can't use the second derivative test. Only works with these two combinations. Okay? Otherwise, you should know concave up, concave down, point of inflection. Most people, if you get point of inflection wrong, is because you forget. F double prime of x has to equal 0, or f double prime of x has to equal undefined, and f double prime sign change. Very quickly, how many points of inflection does that have? It's a quick question. Not lots. How many? So, I'm going to have you raise your hand if you think it's 0. Raise your hand if you think it's 1. It's a quick question. Raise your hand if you think it's 2 points of inflection. Raise your hand if you think there's 3 points of inflection. So analysis. This is the stuff that I feel like you guys are supposed to know, you don't know. So second derivative equal to 0, there's 3 zeros. Do we agree with that much? Okay, so your possibles are 4, -2, and 1. These are extremely important. Even powers, signs don't change. Therefore, point of inflections happen here and here only. Won't change here. Okay? Nice to know that, isn't it?